Okay, colleagues, greetings. So, I'm gonna continue our discussion of philosophy of physics. So, basically today, we're gonna try a different format. This is basically gonna be a Q&A session. These are, I'm gonna try to go through some of the questions that usually come up whenever we discuss this stuff in class. So there's gonna potentially be even less organization this time than compared to previous videos. And again, I remind you, this is in many ways is a work in progress for me. I'm preparing to do this stuff in a more systematic fashion in September. So I have a whole bunch of topics. So this video is basically going to go on until it doesn't, so maybe for about an hour. And I just want to go through like a shotgun list of topics. One thing I suppose I want to, well actually, yeah, maybe one thing immediately I want to begin with is that, you see, this idea that we've been talking about, that we've been mentioning, again, according to our best contemporary physical understanding, the universe is not going anywhere, right? It's moving towards a heat death. And even if, again, I mentioned last time that even if beyond the heat death of the universe, you can have a quantum fluctuation that starts a new universe. Or maybe you can have, again, within Penrose's cosmology, a conformal transformation and a new eon, a new universe starting that way. Or if you have infinite inflation, maybe you can have a patch, like another universe nucleating, right, in a different place. So what I'm driving at is that there's a possibility that, again, we have our observable universe, but there's a possibility that outside our observable universe, beyond our observable universe, in time or in space, there's going to be something interesting going on, right? But in many ways, it doesn't change the fact that whatever we do as humans is overwhelmingly likely to be completely lost in the grand scheme of things. We are not going to have any kind of lasting impact, right? And that's a big difference. That's a big change, right? The ancient worldview was that this world is made for us. The somehow the universal source of all existence, God or something, right, cares about us. This universe is made for us. If you have a pimple on your forehead or a splinter on your toe, that plays a role in the structure of the universe, right? But according to this mechanistic worldview, and especially in light of this coming heat death, right? What happens is basically that there could be no lasting point to anything. And again, this is why I keep talking about how post-structuralism, Foucault, Lacan, but also some topics from Buddhism and also some issues from cosmology all speak to the same issue, right? And especially I could refer to Nietzsche with his ideas of eternal recurrence, right? So for Nietzsche, there's a very, very important difference between the Christian, let's say the Christian or the Judeo-Christian worldview, in which, yes, your life right now may be bad, and this is what he calls the nihilism of Christianity, right? But then you die, and then something happens afterward, something much more important, the judgment, the second coming of Jesus, the resurrection, right? And Nietzsche had this idea of eternal recurrence. No, imagine that this universe is not going anywhere. And his way of phrasing this was in terms of, again, this is maybe has some connection to Poincaré's recurrence principle, right? So an actual principle in physics, which may or may not hold. It's a complicated story, right? There are interesting constraints. But as a possibility, again, this notion that, again, the universe is not moving anywhere. It's not. There is no lasting progress. Either, as I've been mentioning, ends in a heat death, or even if it doesn't end in a heat death, there's going to be a certain like cyclical structure such that, again, all of the horrible things, the murders, the genocides, the raping and the robbing, and the death and the destruction, all of the suffering is going to continue indefinitely, right? So, and in this sense, again, I feel that there's an interesting, again, parallel between the kind of worldview that science, philosophy of physics basically teaches us, and certain interesting issues, again, in Buddhism, but also maybe in Schopenhauer, maybe in Nietzsche. Do I want to pursue this right now? Well, maybe no. I want to focus more on the physics side. So let me talk about some of the issues I have on the slide here. So maybe let me start with this notion of God being incomprehensible. You see, this is a very difficult topic for me to talk about, but I feel it's a very important topic. See, whenever students talk about God, I feel that, especially first-year students, I feel that many of my students lack imagination, right? Am I an atheist? Am I a believer? Do I believe in God? That's a very, I want students to appreciate the difficulty of this question. You see, for me, figuring out whether time or space are emergent, that's a difficult question. For me, figuring out, again, if the universe had a beginning in time, or whether maybe it didn't, right? That's a complicated question. Mm-hmm. And the question, the question of whether we live in a simulation is a difficult question. Or maybe we are Boltzmann brains. I want to talk about Boltzmann brains in a second. That's a difficult question, right? But the question of existence or non-existence of God is an even more difficult question, right? So in an important sense, I want to say, it's not up to us to judge about these things. But, as far as one can tell, if some kind of divinity exists, like a principle, a unified single principle of the universe, right? If you think of the Neoplatonic one, a unified single principle of the universe, maybe that kind of thing actually exists in some sense. Is it conscious? Does it care about us? Does it have a certain kind of standard of morality? You see, these questions are important to think about. So what I'm driving at is that the answer to the question whether God exists or not is not an interesting answer in its own right. A much more interesting question is what kind of thing, what kind of entity is God? Because on some definitions, if you take Anselm's ontological argument, the universe kind of counts as God within Anselm's ontological argument. Do you believe that the universe exists? Okay, yeah. So what? What is the consequence? What is the conclusion? So, but on the other hand, I feel that studying ancient philosophy, studying Indian philosophy, studying Chinese philosophy, and now studying philosophy of mathematics and of physics helps us appreciate the complexity behind this issue of God, and especially this incomprehensibility of God. These different ways in which God can exist, right? And I have this Hobbes versus apophatic theology. I had a friend who's a theologian, and he was listening to my lecture on Hobbes, and he said, Hobbes says that God is incomprehensible. So what? Classical apophatic theology also says that God is incomprehensible. And my response was, again, that most of the theologians I know lack imagination. When we say God is incomprehensible, literally means God is incomprehensible. Maybe God has no values. Or maybe God values carnage. Or again, this silly example that I give, students tell me about this game called Saints Row. And in this game, Saints Row, you can feel free to double check this. The God of this universe wants you to just cause harm and misery and carnage to everybody. And if you just run over innocent pedestrians, the God of that universe grants you immortality and infinite ammo, right? So when God's incomprehensible, opens up all sorts of possibilities that I feel people don't keep in mind, right? And this is the real reason why Pascal's wager is such a bad argument. Because it's not a choice between, either you believe in God or not believe in God. There's literally an infinite number of ways in which you can believe in God, some of which you cannot even imagine. Anyway, so let me talk about something else. Yeah. Well, this is, partly, me brainstorming, partly this is based on, again, questions that students often ask. Yeah, okay, let's talk about Boltzmann brains. So Boltzmann brains. So what is a Boltzmann brain? So in general, I would say this falls into the rubric of what could universe be? What could the observable universe be at bottom, right? And what is the ontological reality? And it's you could imagine some sort of naive realist scenario which says, well, actually no, our perception of the universe is approximately accurate. and this would be kind of naive realist assumptions about the universe, right? Like, things exist, and let's say time is real, space is real, time and space are real, and in some sense objective, etc. Like the way we perceive the world actually objectively maps onto the fundamental reality. But then you could have all sorts of other possibilities, right? So you could have Cartesian evil demon, right? So there would be this notion that actually all the world is just a dream. So the world is just a dream, which is induced by this evil demon or something like that. Those of you who know about Descartes will be familiar with this argument. But yeah, there's another possibility would be that this universe is a simulation. And again, I mentioned last time that ancient philosophers could not really imagine this, or early modern philosophers could not have imagined this. I mean, again, Pascal, when he talks about Pascal's wager, does not really have in the cards when he talks about whether there's a God or no God. He doesn't allow for the possibility. Or whenever you talk about, let's say, problem of evil, whether God is good, whether God is providential, most philosophers of the past do not allow for the possibility that all of this might be a simulation, right? And this is an argument that is due to many people, but most famously to Nick Bostrom. And Bostrom actually has this argument. He says that as computational power increases, and we actually do a lot of simulations of the universe, right? In trying to understand the universe, right? And he says that as power increases, as computational power increases, we're going to be doing more and more of these simulations. And he says, if it is possible to simulate conscious beings, we do not know for sure, but it's the guess is as good as there's nothing to rule this out. That it would be possible to perfectly, Turing test, right? Turing indistinguishability. Maybe it would be possible to simulate a conscious mind on a computer. And if that would be possible, then it's like imagine we do some kind of simulation when we try to test our physical theory, and as we do this simulation, actually within our simulation we simulate a conscious being, and a conscious being is brought into existence. Now, we do not know if it's going to work this way. This is the strong AI, weak AI. This is the hard problem of consciousness. But as a possibility, if it could be possible to simulate and bring into existence a conscious agent, it would kind of like a back of the envelope calculation would lead you to believe that actually there would be more simulated universes than real universes, right? And so Bostrom has this argument, which I'm not saying I believe this argument, but it has a certain plausibility to it. And the argument basically would be that of all the conscious creatures of the universe, the vast majority would actually be simulated. So it's kind of an anthropic selection type argument, right? So it's not bulletproof or anything, but it's a certain tendential, circumstantial reason to believe that, right? That we actually live in a simulation. And you could say it's a version of Cartesian evil demon argument. Now, I want to talk about this. I want to say I find this a plausible argument, as plausible as arguments get. Now, Sean Carroll, and I refer to Sean Carroll a lot, as you have noticed. Sean Carroll has kind of a counter argument to this argument, because he says that if we assume that computational capacity is limited, and there's some reason to believe, because as you go deeper down the scale, at least within our universe, you run into certain limits, energy cutoffs. So it's like, if you think about this wonderful complexity that we see around us, there's a size limit. Like you can make complex, interesting stuff out of chemical molecules, but it's not clear if you can make complex and interesting stuff, let's say on the level of subatomic particles. So you can have chemical life, like atom-based life, but it's not clear if you could have quark-based life. And there's some reason to suppose that, again, on the level of subatomic particles, this kind of complexity is impossible. So within this line of reasoning, the notion would be that if you do these kinds of simulations, at some point you run into hard limits, right, of computational capacity. And so you have a universe and within this universe there's a simulation. Within the simulation there's another simulation. Within a simulation there's another simulation, like Matryoshka dolls, right? Russian dolls. Simulation within a simulation. And so Carroll says that this would actually lead you to believe that if we lived in a simulation, our simulation would be fairly low resolution. Is this a watertight? Again, and it's an interesting counter argument to Bostrom. Of course, it's based on assumptions. Bostrom's argument is based on assumptions. But like what I'm driving at is that I feel that the simulation argument should be on the table and should be taken seriously. Like as you go around your daily life, if you're a serious philosopher, I feel that you should take the simulation argument seriously. Now, I don't think, I'm not saying that it's likely that we live in a simulation. I wouldn't bet on it, but it's certainly a possibility that cannot be ruled out. So the Boltzmann brain, I'm not sure if it's an easier or a more complicated idea. Kind of, you can see, so all of these are alternatives to naive realism, right? So one is Cartesian demon, the other one is simulation, the other one is Boltzmann brain, and they're all kind of similar because they say that what we perceive as reality has actually nothing to do with reality as it really exists, right? So the Boltzmann brain story goes like this. So this is something I've been walking around, and this is kind of a big topic, and Sean Carroll likes to talk about this. He has this wonderful picture, which I've shown you before, right? So this would be kind of a story that in the early universe, we have low entropy and low complexity. And so complexity follows this upside-down parabolic trajectory, and entropy simply increases over time. Now, entropy is a degree of disorderliness, right? And so Ludwig Boltzmann, who's one of the founders of, he's a very important figure in physics, right? And he's a key figure in theory of thermodynamics, right? So what Boltzmann actually says is that the law of increasing entropy has a certain statistical underpinning, right? That if you take a system, there are few ways for the system to be orderly, and there are many more ways for the system to be disorderly. So if you imagine a system simply like evolving through some degree of randomness, again, it's like it is likely that you go from low entropy configuration to a high entropy configuration. Let's take an example. You take 10 dice, and you arrange them like all sixes, are face up. All sixes, 10 dice, all sixes, right? And now you just randomly shuffle them. What is the chance that, again, the entropy, the randomness is going to increase, right? So there are far more ways for the dice to be arranged in more random fashions, not this special prepared state where all are sixes, right? And so by this reasoning, again, so the idea that entropy increases, and this has to do with the fact that, randomness on some level is involved. Again, when I talk about randomness, I feel that, again, I have to say that it's possible to unify, to reconcile this emergent randomness, or I should say apparent randomness, with the underlying deterministic forces, right? So the universe can be deterministic, and still in a deterministic universe, you shake a box full of dice and they get more disorderly. So in this sense, randomness, or chaotic behavior is completely compatible with underlying determinism. So it's like you could say there's only apparent chaos, but still. So the idea of down the line, idea of the Boltzmann brain would be that things evolve towards greater disorder. But if you look at early universe, actually the early universe is an incredibly orderly place. This has a lot to do with gravitational arrangement, gravitational smoothness of the early universe, that the universe is smooth and not lumpy. It doesn't have black holes, for example. It's a whole separate story. But the idea is that, the early universe appears to be incredibly fine-tuned. Early universe appears incredibly finely tuned in terms of low entropy. And there are ways to try to solve this, but one immediate way you could have is you could say, well, let's imagine. So one solution would be to imagine, let's say it was just a random fluctuation. So it's like that the universe was actually disorderly, but then through a random fluctuation, you have a patch of space which emerges in this orderly configuration. But the problem is that if you have this huge, the observable universe is close to 100 billion light years across today, right? So the observable universe is fairly big. So in order to produce something like us, something like you and me, you don't need this huge patch of space. So again, it's kind of it's called anthropic reasoning, right? So and anthropic reasoning has to do with, again, ideas of selection effects, and what are the minimum conditions? What are the minimum conditions for the emergence of conscious observers? Right? And so the idea would be that if you think that the low entropy of the early universe was simply due to a random fluctuation, and these fluctuations are possible and they happen, it means that this would have to be a fairly big fluctuation. It would imply that smaller fluctuations happen much more often, right? So it's like air molecules in this room, right? There's a chance, if they just move in this Brownian motion, there's a chance that all the air molecules would stack up on one side of the room and I would suffocate. Now, this chance is incredibly tiny, so I don't have to worry about this, right? But, all the molecules stacking on one side of the room is unlikely, but let's say all the molecules, half the molecules stacking on one side of the room, that's much more likely, right? So a smaller fluctuation is more likely. So the conclusion is that rather than fluctuating an entire observable 100 billion years universe into existence, you could simply fluctuate only a galaxy in existence, right? Like a Milky Way galaxy. Or maybe you could fluctuate, and that's the whole point, maybe you could simply fluctuate randomly a brain into existence. So the notion would be that you have some kind of thermal equilibrium heat death vacuum in which you simply have quantum fluctuations. And a brain with memories, perceptions, randomly just fluctuates into existence. Given enough time, given the laws of probability, it's reasonable to suppose that these things happen, right? So, but the idea would be then that all of my perceptions right now are completely false. They misrepresent reality. So again, the feeling of color, the feeling of coldness, the feeling of water in my mouth, all of these are a product of electrochemistry of my brain. And one hypothesis is that my brain is stimulated by the world outside and I have these experiences. Another possibility is that my brain, and only my brain without my body, has fluctuated into existence momentarily. And maybe in the next moment will fluctuate out of existence, right? But it's an updated version of the Cartesian evil demon scenario. But Cartesian evil demon is a simple just so story. Descartes says, well, let's just imagine there's a demon. But Bostrom offers arguments for his simulation hypothesis. And Boltzmann also offers arguments. I think, don't quote me on this, I think it was Arthur Eddington who actually made this explicit conclusion and talks about Boltzmann brains. And so what cosmologists very often would do, one potential, so Carroll has a counter argument against against Bostrom. Carroll also has a counter argument against Boltzmann brains. And the counter argument has to basically involve creating or fixing, arranging the laws of physics in such a way that it is easier to make a universe than a Boltzmann brain. So if everything we believe about the universe, this outdated formula, which I confessed last time is not exactly accurate because it doesn't include gravity. So if this formula is right, if there's reason to believe this formula, then Boltzmann brains in principle might happen, but they happen so very rarely, they're much more rare than ordinary observers like you and me, right? But arriving at this conclusion entails fixing the parameters of your physical models in certain special ways. Again, for example, in the theory of infinite inflation, or in Penrose's conformal cyclic cosmology, normal universes occur far more often than Boltzmann brains, right? So, why am I talking about this? It's like this is a Q&A, no particular reason, but I feel that these ideas come from philosophy of physics, and they're just interesting thought experiments I wanted to mention. Because usually, in regular classes, there's not enough time. There's not enough time to go into these details. I see some people in the chat, thank you for your company. Anyway, so let me see my list of topics. What else did I want to talk about? It's a complicated issue that has to do with do we understand the laws of physics, the everyday laws of physics? And here's the issue. So, first of all, I keep talking about how there's this interesting duality of uncertainty and certainty when it comes to science. So, on the one hand, the foundations of science are completely uncertain. Like, science is not built on any kind of solid foundation. On the other hand, I feel that there's an overwhelming pragmatic reason to trust the science completely. So, I wanted to talk about some things that follow from our understanding of science. So, one has to, if you imagine our everyday regimes, so what I'm driving at is that we apparently we understand the everyday physics, very well. So when I say everyday physics, what I mean is kind of the normal circumstances. Like, if there's a false vacuum of the Higgs field, or if we collide with another universe in a different dimension, right? All bets are off. But there's a reason to expect that the models that we have that describe reality are fairly complete within the given domain of applicability, right? And so, in order maybe to illustrate this, I wanted to talk about Feynman diagrams, and especially the crossing symmetry of Feynman diagrams. So this is the simplest. Well, this is not the simplest Feynman diagram. It would be a simpler diagram if we erase the stuff on the right side. Can I erase? I wonder if I can do this quickly. It's not going to be easy. Well, anyway, so you have an electron and a positron. Yeah, you can see my mouse, right? So you have an electron and a positron coming together. So time flows from left to right, and they annihilate and emit a photon. Now, the reason why photon then emits a quark and an anti-quark is probably because there's a lot of energy in this collision, and maybe there's too much energy in this photon, and it's likely that the photon will actually decay into quark and an anti-quark. And maybe it's a virtual quark, I guess, within this diagram. But that's not really important for our purposes. So this is the famous Feynman diagram. So again, so you take an electron and a positron and you annihilate them into a photon. But the crossing symmetry tells you that you can rotate this diagram. And so, for example, you can take let's say a photon, and you can make a photon decay into an electron and a positron. Or maybe you can have a quark and a gluon come together. A quark and an anti-quark come together, emit a photon, and then they would decay into a positron and electron pair. So you see, the point of this diagram is that it can be rotated. My physics is a bit rusty, so there are other rotations you can perform. But again, the point is that we've done experiments, right, at Large Hadron Collider. And so within the regimes of the Large Hadron Collider, so unless something catastrophic happens, the standard model seems to be fairly robust. Apparently it's fairly robust. So these are the forces that we have. So gluon is the strong force, W and Z bosons is the weak force. H is the Higgs mechanism, right? Photon mediates the electromagnetism, and there's also supposed to be gravitational force, which is mediated by hypothetical particles, which are gravitons, which probably exist, but we cannot detect them because the energies involved are far too high. So kind of plus gravity. But the idea is that, it's an interesting thought that goes back to the Milesians and to the ancient Greek philosophers, that anything can be made out of anything. This is basically what we do in a Large Hadron Collider. So you can take gluons, you can smash them together and make Higgs bosons. Or you can smash Higgs bosons and make, weak bosons. You can take, again, basically what Large Hadron Collider does is you take atoms of hydrogen, you strip electrons away from them. So you end up with 2 protons. And you accelerate these protons at great speeds, and you smash the protons together. Now, protons are composite particles. They're made of quarks and gluons, right? So when they smash, it's not a very clean collision. But the point is that if you smash them enough times, and there are something like billion collisions per second or something like that. So there's a huge number of collisions in the Large Hadron Collider. Don't quote me on that. But there's a huge astronomical number of collisions, right? Eventually, you end up making everything that's possible to make. Because again, the picture of the universe that underlies the Standard Model is that you have these quantum fields, and presumably each of these particles has a quantum field. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17. 17 quantum fields, maybe more. Maybe antiparticles have their own quantum fields. Maybe there are other quantum fields which we haven't discovered yet. But the idea is that this model governs everyday life. Like, we do not expect any other interactions to really affect everyday life. So maybe there are other fields, like we're looking for dark matter particles, right? So dark matter could be a part of this model, an extension of this model. But the idea is that dark matter interacts so weakly with this picture that we have not been able to discover it yet, right? So like we've had particle colliders, and each new collider has greater and greater energy, so we have a pretty good understanding of what are the energy cutoffs. So the idea is that if there are more particles in the universe, or if there are more forces in the universe, they do not affect our life under normal circumstances. So basically, the moral of the story, the kind of philosophy behind this kind of approach, is that the laws of fundamental physics are completely understood within our everyday regime. So if we want to explain consciousness or morality, right, we do not need to postulate new forces of nature. If new forces of nature existed and were strong enough to affect you and me, we would have already detected them. Basically, the idea of crossing symmetry of Feynman diagrams is if something affects you, you affect it back, right? And you could say, well, it's just an assumption. Well, maybe yes, maybe no, but it's a fairly well-tested assumption. Let me mention a couple of corollaries from this picture. So one thing that happens within the Feynman diagrams is that if you have a particle, if it can decay, it will decay. Sometimes particles are stable and therefore cannot decay, like electrons don't decay. But if a particle can decay, it will decay. So this rules out certain interesting possibilities. I don't want to say rules out, but places hard constraints. So sometimes people ask me, especially if you imagine time travel or faster than light travel, can you have negative mass? Well, you see, the problem is that if you could have particles with negative mass within Feynman diagrams, then normal matter would be constantly decaying into this negative mass matter. Or let's say if you could have negative energy, likewise, normal matter would be able to decay by producing this negative energy. So it's a little bit like this ancient problem of something coming from nothing, right? So again, the ancient Greeks had this principle that nothing comes from nothing, right? And kind of the sort of the philosophical reason for that is that if something could come from nothing, then think about this. There's more or less an infinite amount of nothing around us in the tiniest patch of space you could imagine. There's an infinite amount of nothing. So even if there's a smallest probability per unit of time that nothing would generate something, right, then the universe would just overflow with things, right? And I feel that there's kind of a similar idea between the two. Again, I'm not sure if this is helpful, but I just wanted to talk about this. I suppose I also should mention that within Feynman diagrams, we talk about these particles and waves, and then there's this unsolved problem as to whether the universe is made of particles or waves. And I kind of want to stress that in the 21st century, we still do not know the answer. Our best models today, which are, the standard model of particle physics, and is based on or instantiates quantum field theory. And so in quantum field theory, what is fundamental are the fields, and everything that exists are the fluctuations in these fields. And so the idea is that we see particles, but that's a certain kind of an illusion, because the differential equations that govern the behavior of fields only have integer solutions, right? So, and that's why you can see 0 electrons, 1 electron, 2 electrons, 3 electrons. You cannot see, let's say, half an electron. But this results from the fact that, again, the differential equations underlying this stuff does not have integer solutions. But at bottom, electron is not an object, but electron is a wave, is a fluctuation. Now, that's a possibility. There's another theory, which is probably much less elegant, but this is pilot wave theory. And within the pilot wave theory, which was started by Louis de Broglie and then continued by David Bohm and other people, John Bell, famous physicist, was a big fan of pilot wave theory. You have waves, and then there are particles riding on waves. So the notion that fundamentally particles exist is not ruled out yet. But my perception from listening to physicists is that the vision of the underlying reality that is favored currently is that, again, the universe is made of waves, but particles are, technically speaking, not yet ruled out. And so talking of particles, let's say within the Feynman diagrams, is just a useful heuristic approximation to talking about waves. But actually what exists are waves. So these would be, again, there's an up quark field and a down quark field and a Higgs field and a photon field and a gluon field and a W plus field and a Z field and a muon field, muon field, tau field, muon neutrino field, tau neutrino field, right? And particles are certain kinds of useful heuristic ways of talking about what these fields do. But ultimately fields vibrate, fluctuate, and these fields are all connected, and these are the lines that tell you how the fields are connected. So you could say that all of these fields, 17 fields, are subfields of one another, right? And that's the picture that we get at the fundamental level. And in this sense, again, you see, even something very simple, as simple as a hydrogen atom, is not a stable thing, right? You have, if I could draw, I draw this. I like to draw this on the board, but it's like you have quarks and gluons, quarks exchanging virtual gluons, which holds them together, like this intricate dance. And this creates the illusion of the stability of the proton. And then between the proton and an electron, there's a virtual photon going back and forth, right? And so, again, a certain kind of dance. So, a fluctuation in the electron field sends vibrations through the photon field, and it affects the interesting system of vibrations between quark and gluon fields, which constitutes a proton, right? And so this intricate dance of vibrations going back and forth gives an illusion of stability of something like an atom of hydrogen, right? But the idea is that underneath that there is no stability. Kind of process ontology. Maybe I should write this word. What is fundamental to the universe is processes, not stable things, right? And the idea is that even if there's no stability on the level of fundamental physics, then obviously there's no stability on higher levels. Again, if strong emergence is false, and if weak emergence is true, again, I just mentioned that, again, within this kind of philosophy, you don't solve the problem of consciousness by postulating different kinds of matter or different kinds of stuff, like dualistic kinds of stuff, right? But what you postulate is, the working hypothesis is that the interactions between simple things give rise to more complex things. Again, this irreducible complexity that I talked about last time. It's possible, again, to generate from simple rules a chaotic and unpredictable system, which is much where the whole is bigger than the sum of the parts, right? But ultimately, the behavior of the whole is reducible to the sum of the parts, right? So this would be the idea of how you solve the problem of consciousness, at least the so-called easy problem of consciousness. How does consciousness actually function, right? But the idea then would be that there is no unity on the level of individuality. And again, Nietzsche talks about this, and David Hume talks about this before Nietzsche, and Buddhists talk about this in ancient times, right? So the notion that the continuity of the self is just an illusion, right? There are homeostatic processes that, in a certain kind of pattern, repeat themselves over and over and over and over again. But underlying that, there is no real ontological stability. And again, you resemble the kind of person you were a moment ago, but you are not the same person in any serious metaphysical or ontological sense. Like, again, your relation to yourself a moment ago is akin to your relation to your identical twin. You look similar, but you're not the same person, right? Kind of interesting implications for views of personal identity and that kind of stuff. Okay. Let me also mention that, again, I have this talk about quantum effects in biology. Again, you see, as far as we can tell, when we look at these kinds of Feynman diagrams, in every experiment we have done, our basic physical models have been vindicated. We have never seen a biological experiment violate laws of physics. We have never seen a neurophysiological experiment violate the laws of physics, right? So in this sense, again, I talked about this last time, strong emergence appears to be false. Or at least there is no experimental evidence to suggest otherwise. Yeah, so I suppose another thing I guess I kind of want to mention. Do I want to talk about quantum mechanics and determinism? Well, quantum mechanics. Quantum mechanics is a complicated topic and a hobby horse of mine. So I don't know. All sorts of thoughts come to mind, but maybe not necessarily anything in particular I want to. Well, anyway, I feel, again, I promised that this might be chaotic, and I said that this probably will go on until it doesn't. Maybe I'm thinking maybe I should take a break here, because I sort of ran out of ideas I can talk from the top of my head. Maybe I should think about this some more. So it's like I'd rather be talking and saying something interesting than just sitting and thinking about what else to talk about. So anyway, colleagues, I hope this gave you some food for thought. Definitely, I always want to get to these topics, and I'm not doing them justice here. But at least I'm, for those of you who want to do your own research, because there's plenty of wonderful material available on the net, right? At least I hope I've been able to stimulate your curiosity. So if there's anything you want me to follow up on, feel free to write, in the comments, for example, for instance. Otherwise, I'm gonna go back to the drawing board, think of some maybe other things I can talk about. And until next time, stay safe, take care, and thank you for your company.